I did a Pathways internship with the USGS Earthquake Science Center over the last year. And my internship project was to create some tools to better understand what's going on with earthquake sequences so we can improve aftershock forecasting from the USGS. Okay, I did press the right button. So I'm going to start off with like an introduction to the USGS style aftershock forecasting, and then I'll use that to segue into the actual software that I developed. So the USGS issues the aftershock forecast for domestic events for magnitudes 5 and greater, and for international events that might trigger humanitarian response, like for Puerto Rico. These forecasts felt potentially damaging aftershocks in the next day to next year, and they're updated quite frequently, about 75 times in the first year. There are quite a few entities that use these aftershock forecasts, namely emergency managers, FEMA, state governments, other federal agencies, lifeline operators. But I think a lot of the like groups that use this these forecasts are the public, because we want the public to be informed of what's going on. So aftershock forecasting, as we all know, is important because we want to provide situational awareness to what's going on. We want to increase public resilience, prioritize response and recovery operations, and increase safety. So the USGS currently uses the Riesenberg and Jones model that I think we're all pretty familiar with. But to recap, this equation describes the rate of aftershocks of at least some magnitude since some time after the main shock. There are three components, namely the Utsu relationship, the Gutenberg-Richter relationship, and the modified Amori law. All of these play a role into creating the aftershock forecast. The USGS creates initial forecasts using generic parameter values defined by Page et al. 2016. And then uses Bayesian updating of parameters, or does Bayesian updating parameters using generic distribution as a prior. So as we learn more about the sequence, we can reduce the uncertainty and provide a like a more fine-tuned forecast specific to this earthquake's behavior. And that's what eventually leads into a sequence-specific forecast with parameters specifically for this sequence. It's a lot of S words in that. So the figure on the slide here is, I guess, showing an example of this evolution of parameters over time. So the black line at the bottom of the plot is showing the initial, in this case, A-value distribution, and we say that's a very broad distribution. And then as we progress through time, this peak actually like narrows in on a specific value that we determine as the most likely parameter for a sequence. A lot of words. So to help visualize these aftershock forecasts and better understand, at least visually, how they are reflecting an aftershock sequence, we can make a plot. So this figure is for the magnitude 8.2 Chignik earthquake that happened at the end of July last year. And this is a log scale of number of earthquakes above magnitude 3 over time. The black line is the cumulative number of earthquakes above magnitude 3. And each of the vertical lines is a forecast. And the height of the line is the 95% confidence interval for the number of earthquakes that we expect to happen. These lines are grouped in time and are colored by their duration periods. So, wow, I'm like, you feel nervous, it's fine. So the green is a day, orange is a week, purple is a month, and pink is a year. And these are vertically offset to account for the number of earthquakes that have occurred before the forecast began. And these are plotted at the end of their forecast interval because we want to know how many earthquakes have occurred within the forecast window. And this is, I guess, a sneak peek of one of the figures that's actually in the viewer. So the OAF viewer uses predominantly the Riesenberg and Jones model, and we would like to, in the future, incorporate equations to show ETAS forecasts as well. And I'm showing screenshots of the viewer because trying to do a live demonstration is already way too much stress, earthquake pun intended. But if people want to see a live demo of it during the break, definitely come find me and we can make that happen. So when the OAF viewer is open for the first time, there's a global map of all earthquakes that have forecasts issued for them. The location pins are colored by the number of aftershocks above magnitude 3 since the time the forecast was updated. And then when you click on one of these location pins, you get a pop-up with basic information about the sequence. And you also get a link to the USGS event page where you can learn more about the sequence. So I guess the basic structure of the viewer is at the top of the screen, you have tabs that show different visuals, and in some cases, like data tables, so you can see all this information in list format. On the left-hand side is a sidebar where you can customize what you are seeing in the main part of the screen. And then obviously the main part of the screen is where you see the visual. So once we click on a sequence, we get to a zoomed in aftershock sequence. And it's a little weird that I clicked on the Chignik earthquake and then went to Antelope Valley, but it's fine, we're improvising. So this is the magnitude 6 Antelope Valley earthquake that also occurred in July. The aftershock sequence is colored by the network that issued the authoritative magnitude, and the size of the point is proportional to the earthquake's magnitude. The red circle is the aftershock region, which is the spatial extent of the aftershock sequence. And then the gray circle is an expanded search radius, which is used to make sure that all the aftershocks are actually being accounted for by the forecasting. So this and the global map are really useful for just providing some geospatial context to the sequence. And this can be useful for telling the public like just how much area could be affected by aftershock sequences. The first plot that is made when we go to the magnitude time plots tab is a magnitude time plot. This plot is really useful for just identifying trends and patterns in the data. The vertical axis is time, the horizontal axis, in this case, is sequential event index. And this is an option in the OAF viewer to help spread out the early aftershock sequence. The points are again colored by the network that issued the authoritative magnitude, and the shape of the point is the magnitude type, or how the earthquake magnitude was determined. This plot includes magnitude of completeness, which is the gray line starting at magnitude 6 and goes horizontal. And then the two vertical lines on the right-hand side are the time the last forecast was updated, which is the dashed line, and the solid line is the end of the available aftershock data. On the same tab, we can also look at the cumulative number plot for the sequence. This is same vertical axis, days after the main shock on the x-axis, and then a second vertical axis for the two red lines. So the solid red line is the cumulative number of earthquakes above magnitude of completeness. And the dotted red line is the Riesenberg and Jones aftershock model. And this plot is really useful for comparing the model to the data to see how well the model is reflecting the aftershock sequence. This plot also includes the aftershock scatter plot, as well as magnitude of completeness. And the reason this was added in was to help make sure that abrupt changes in the in this decay curve are actually expected and not due to like a programming error or a Comcat issue. But if you want to just look at the cumulative number lines, there's a checkbox option to exclude the aftershock data from the plot. And the main difference between this plot and what would happen if you uncheck that box would be that the cumulative number scale moves to the left-hand side. Next would be a magnitude frequency plot, which shows the log number of events over magnitude. The solid triangles are the cumulative number of earthquakes above a minimum magnitude, and the open triangles are the total number of earthquakes per magnitude bin, and these have a bin size of 0.1. The vertical line on the plot is magnitude of completeness, and then the red line is the Gutenberg-Richter distribution calculated using the forecast data, and the black line is the GR distribution calculated using the data. So this is another way to compare the model to the data and see what's going on. One of the key things about this in the sidebar, we can change magnitude of completeness and also the b-value slope to see if there's a set of parameters that better describe what's happening in the aftershock sequence. So the second to last plot is a forecast success plot that is similar to what we saw earlier in the presentation. So I won't spend a lot of time describing the plot on the bottom half of the screen. The only difference is that this is looking at the 6.2 Petrolia sequence that happened at the end of 2021. And at the top of the screen is actually, I think will be the takeaway from this plot or from this slide is this is showing the percentage of successful forecasts. So this is basically comparing the number of forecasts that have been successful to the number of completed forecasts. And the way we're describing success is simply, do the observations lie within the 95% confidence interval, inclusive of the limits of that confidence interval. So graphically or visually, if the black line intersects one of the vertical lines, forecast was a success. Fantastic. So this is a quick way to see how well the USGS forecasts have been doing. And if there are no completed forecasts yet, then that entry in the table is left blank. And with this plot and with the magnitude time plots, we can also look at the contribution, or I guess not with this plot. At least with the forecast success plot, we can look at specific models by using the checkbox options in the sidebar. And we can also look at the different forecast duration periods. So if we're interested in what's going on in the early sequence, we can fine tune our sidebar options to like focus on that section. And then the last figure that's created in the OAF viewer is forecast parameter plots. So these are showing the temporal evolution of aftershock parameters. And this plot, I think this is my favorite plot because you can look at any combination of parameters and see like how one might be influencing the other. And it can also be compared to the forecast success plot to see if the change in parameters is also improving the forecasting. So the points on this plot are colored by the forecast model. And then the error bar is one standard deviation. And then This plot also, or this window also shows the most recent forecast information just beneath the tabs at the top of the screen. So you get the name of the model and the different parameters. And for everything but the maps, if this is information that's worth saving, there's a little save plots button in the upper right corner of the window. And then a button that is way more impactful when doing a live demo and doesn't do it justice as a screenshot is the view another sequence button, which takes you all the way back to the global map where you can go and view another sequence. So this would be a really useful tool for Aftershock forecasting, not only because we have all the figures that we just looked at, but we also don't have to sit there and like press the same button over and over and over again to look at different sequences. We can just select the time range and then look at whatever earthquake sequences we care to look at within that time range and not have to reset everything. Yeah. So there will be a paper on this. I wrote, Andy, Michael, and I wrote a paper to SRL that is in review, and the software that creates all of this is also in review and would be available on code.usgs.gov. And I want to give a special shout out to the OAF team at the Earthquake Science Center. Everyone on the screen provided a lot of really insightful and wonderful discussions that helped make all of the like small little changes and like additions to the viewer possible. And if there's plenty of time, then I can take some questions.